Sound check?
Good.
Well, it's lovely to see you folks again because it has been a very long pandemic for very many of us, and it's great to actually be able to do this in person again. So thank you very much to the organisers for that. I want to try and change tack a little bit here and convince you that trans-Neptunian studies is relevant not just to our own solar system, but that we can make TNO studies an important part of thinking about the entire galaxy. So this is work with a fabulous team of people, very many early career, and I want to start off by contextualizing why this ends up being important. So an interstellar object in this sense is exactly the same as our TNOs. These are samples of planetary system formation processes. And like TNOs, they last a long time. They outlast their stars. So they are sampling the planetary formation processes, not just all across the galaxy, but the stars that are no longer even here. And to try and understand any of that with the sample that we're going to be acquiring with our surveys, we need a model. So this is what I'm going to walk through today is the efforts that we're making to try and develop this model and the areas where we think we need to push on. So to be very clear, this is what I mean by an interstellar object. It's planetesimal. We see these on hyperbolic orbits when they enter the observable volume. And these are a remarkably interesting population in many ways because they're numerous. We are talking about a few 100,000 objects for our sample in the outer solar system, many of these. This is where all our TNOs go. They go and join this population. And so the interstellar object population ends up being both planetary and galactic. So we have to take into account when we're thinking about the observed population we'll have in our surveys of what's happened in the Milky Way for its star formation history, for its planet formation history, and also how these are evolving in the potential of the galaxy itself. And that's what's going to let us be able to do the kind of inference work that we know and love for the observed samples we have, and vice versa. So we only have two observed objects, right? We don't have survey characterization for the second one. We have some sort of survey characterization for the first one. So the kind of empirical model that we talked about is not yet an option. We need a theory model to start off with. So this is where I'm going to focus, is what do we have? Well, first off, we have to think of these in terms of they actually are playing a feedback cycle in the galactic ecology. They are forming in a planetesimal disk. They are then being unbound from that disk with the kind of processes we've just been talking about. They're then evolving the galactic potential in a dynamical sense, and there may be some level of uncertain evolution in the physical sense, some reddening, maybe not. That's still pretty undetermined. A small fraction of this are going to pass through giant molecular clouds, birthplaces of new systems, and Maura Martin and Norman and myself and Susan Fausner have talked about how they can get incorporated in the collapse of molecular clouds, and we have shown that they do actually follow the gravity down into new systems. So that's the kind of cycle that you can think of. And we're talking about these components as what we're currently determining our Otto-Kahi Oxford model. So once we have the model, this is where it goes. We sample it in our observable body. Our sky surveys perform the sampling, and this is, of course, what Rosemary was talking about on Monday, how we can have this model and pass this through surveys like our SST to obtain our detected sample. And then we'll be able to do the kind of physical characterization that we know about for spectroscopy and everything else. So I'm going to focus on these two parts. The process that we think about with the unbinding and the process of how this evolves in the galactic potential. So this is the two places that we're thinking of for this model. This is to size scale in case you're wondering. And what I'm talking about when I say the unbinding and the evolution is particles when they suffer these dynamical instabilities and they leave the system? What velocities do we get imparted to them to be able to work with? Where do they go? What's happening to them? And what structures form in that velocity space that then slink through the solar system as they pass in, travel past, come observable, and then go out again? So unbinding, this is something that has been a theme of this whole session, is unbinding events are an important part of our evolution. Now, there's been a nice amount of work thinking about how early this happens and what the kind of velocities we're talking about are going to be like in the early stages, 0.5 to 1 kilometers a second. Maybe when you start doing instability, you can get them a bit further. If you unbind them at the white dwarf phase, when you get rid of the Oort cloud, then you're even looking at slower velocities again. But this is a thing that we have from trans-Neptunian studies that has taught us this is an important process. And so we can extrapolate. We can take this to the whole galaxy and go, yeah, all our planetary systems are giving us TNOs. So when does this really happen? And we can rephrase that, I suppose, in how does the architecture of the system govern that effect? So undergrad student Leah Ortbaum in our group has been looking at this, and we were really inspired by something that Badigan and Walden did in 2017, which was thinking about this in terms of the Safranov number. So this was a research note. This was one of these, let's think about the architecture and can this make it memorable? Well, if you look at this with the current data set, the escape velocity ratio of the system as a function of the planetary architecture, what you find is of the known exoplanets, they don't do stuff. They don't make interstellar objects. But on this side, we know there's plenty of detection biases. So sure, the current state of exoplanetary systems, most of the planets are not making ISOs. But the solar system we know and love, that's the circular dots in here, our outer planets have a Safranov number perfectly adequate to make ISOs. So we know there's detection bias in this. So let's take this with a grain of salt and think about what's happening in terms of the disk and the ejection velocities. We did a sampling of disks, so we just put basically a giant planet in the disk across a range of locations, make a disk from 1 to 100 AU, sample it 10 million times, figure out what the ejection velocities are for any particle that would be ejected. If you take a disk and make it a cold classical disk, you get this nice little tight velocity distribution. As you excite the disk, you get much broader velocity distributions relative to where you put the planet. So far, so good. This kind of tracks with what you expect. You put more energy into the disk, you unbind the object, they go off the great more zoom. But this is kind of, not thinking about the main process going on, which is the instability. So we make a lot of little planets, and this took a couple of months to run, so this is still very preliminary. But this gives you some idea of the mass partitioning that we're doing, up to 7 planets, laying these out and putting in a disk between 5 and 50 AU, and then seeing what happens in 10 years. So to put this kind of relatively low physics simulations in context with, say, the NES 40 2024 much more detailed solar system run, we're working with 1.6% of the retained objects in everything we've been talking about this meeting so far. The 93.4%, this is what was donated to the galactic population. And so as a function of these planetary architectures that result after that instability, you actually get these nice, as we came into cluster orbits, you get these nice clusters showing up of different velocity distributions that do track as a function of the planetary architecture. And so we do get some variation across that in planetesimal ejection fraction, how many planets you kick out. It's reasonably chewy, so if you want to go more into that, I'd be happy to show you later on. But this gives you some idea that the architecture, the instability history is going to affect the kind of velocity distribution that we see. So what happens to these now they're unbound? Well, now they're in the galactic potential. And John Forbes, a research fellow in our group, has been looking at this in a lot of detail. So initially they're coming off the stars, and the stars are moving a particular velocity distribution of the galaxy. But one of the nice things that Simone Bourdieu-Smort noticed in 2020 is as they evolve in the potential, you get these streams formed either side of the system, whether it's a cluster of stars emitting its ISOs, or whether it's a solar star. So a lot of work has been put in by John and by Angus and Jack, students in the group, for building this particle simulator in the galactic potential, which allows us to go away from having to do a full numerical integration for all this and write down the semi-analytic argument and then pre-compute a lot of things with that and be able to run this very fast. So I can show you a reasonably low resolution simulation of how this motion of the galaxy happens. So the stars here emit their ISOs, and 3 of them in particular are color-coded for your convenience, so you can see where the strings form. These are stars that have different velocities within the stellar velocity distribution. The sun's orbit is indicated there as yellow. So you can get an idea of just how much you get these strings formed and how the entire galaxy ends up being this woven mass of strings. Now there is more heating that goes into this, but this to first order is the kind of structure that you get coming out of the velocities imparted to these objects coming off. Okay, so let's have a look at one of these individual strings and how that velocity distribution and ejection will affect its formation. So this is also with element particles. This is thinking of this in galactocentric space, and yep, it's changing its axis in the spirit line there. As the stream moves out from its parent system, you get this really interesting dispersion properties as a function of how fast you're throwing the ISOs off the star. So all the things we talk about, the formation processes, will link directly to the kinds of strings we see in the galaxy. And these, of course, are wrapping around as you go. So a string can be puffy, like this one, in high velocity distribution, or it can end up being a low velocity distribution string and stay quite tight and compact its whole time. And so this will then play into questions like, do we intercept a lot of strings? Or are we sitting in a single string or a few strings? And will we actually be able to see an interstellar object from the same star? Will we actually see these strings pretty much? And this is pretty preliminary. At this point, the solid lines are what you get if it comes off, the strings are coming off a cluster versus off a single star. Basically, we do need about a little over 100 ISOs to detect before we start getting into any probability we might see 2 from the same star. So I'm going to finish up with the broader picture that you can take on this, which is, this is kind of the nuanced scale. But what we do have is we have the stellar neighborhood. And this work is led by Matthew Hopkins, a grad student working with me with Chris Lindhout. And what we've done here is combine formation composition models of planetesimals, taking things from beyond the ice line. This is the model of Fish and Battistini 2020, and put this together with Gaia. Because Gaia will need some biasing, because it only has the stars that are alive. But then we can predict those kinematics on a larger scale. So to remind you what this looks like, if you don't think about Gaia every day, because I sure know I think about Gaia most of the time, it's something nice to calibrate things with. This is the kind of velocity structure that the galactic people get to see on a more regular basis. You get this clumpy distributions. And this is the large-scale processes of the spiral arms, of the heating that's going in to form this detailed clumpy structure in the solar neighborhood. Okay, so we de-bias this. We take account of the velocity distributions that I've been talking about. And as I showed you in the earlier animation, you've got the azimuthal mixing going on. So this is what you then get for the ISO velocities. So this is the velocity structure that we have in the solar neighborhood. This is what we're encountering. Now, these nice pumpy distributions, you can see in purple here, we've got one eye nicely in the center of the largest pump. With green, we've got two eye ISO. And this is a really nice feature. We saw Aurora because 1 in 5 ISOs are going to have Aurora-like velocities. We saw 2i because it's the second most likely column. We've got typical objects this way. So a lot of the times this has been modeled with smooth Gaussians in the past. This is the age of Gaia. We have to take these velocity structures into account. And so the ISO speeds that we're seeing, yeah, they're going to be typical, right? This is something where our moving object pipelines have to account for this kind of velocity structure. And I'll finish up with one last prediction, which is composition-wise, depending what planetesimal disk structure model you put in, you can make predictions about what composition of ISOs you'll see and how that will track to where we will see them on the sky. So if we take water mass fraction as an example property, that links to stellar metallicity. And that allows us to form this kind of prediction about where we will see ISOs. So to wrap up, this is where we're starting to form a coherent picture of what the interstellar object population is like. What factors go into it, the ejection velocities, they come off pretty cold. The hot or cold tidal streams will affect how many of these the solar system is passing through. Then they're going to heat in the galactic potential, and that's then going to lead to these big scale velocity structures, which we're going to see, because we have LSST coming up. Thank you.
Questions? Good, thoughts? Joshua?
So thank you, that's actually very interesting. How much are you paying attention to the evolution of the star during this phase? Because the sun will lose 40% of its mass in a relatively short period of time towards the end of the evening sequence.
Yeah, so for the Gaia modeling, the Gaia-based modeling I'm showing here, we are assuming a very early time ejection. So yeah, we're not saying that the star has to evolve and then release the ISOs at the end of the white dwarf phase. That's going to be sub 5%. You know, it's the Oort cloud that's unbinding. We're saying everything's coming off at the early time scale. So in line with the kind of modeling that I was showing from the earlier velocity distributions.
Okay, thank you.
Hi, Joshua Utah. Great talk. I don't know very much about ISOs, so just a clarifying question that I wanted to know was, on your plot you had pre and post, as well as a point that was LSR. Could you describe what are those and what's the difference between pre and post?
Yeah, so this is the pre-encounter velocities, and so the ISO is making a hyperbolic trajectory through the solar system, and then it it's going to encounter the sun, and it's going to have its velocity shifted as a result of that. So one of the arguments that was made with one eye in particular was that its proximity to the local standard of rest meant you could imply things about its dynamical history or its age. What we showed with this work is that argument does not hold water, because here we have a velocity structure, what stellar people would sometimes term a moving group or a craft rather, which is something that is close to the local standard of rest. But you can see quite clearly there's a nice gap. Right? So in that sense, yeah, they're proximate, but the local standard of rest is a theoretical concept that's useful to think about the mean velocity of things in the solar neighborhood.
Thank you.
But yeah, you cannot say that one eye has a particular age. It is not preferred that it is young.
Hey Michelle, wondering how much the structure in this figure
would be altered by simulating 10 stars, not 10 to 2. So the simulation comes from what I could tell from the previous information, something like 100 or a couple hundred stars. How much would you change this by simulating a couple hundred billion stars?
Right, so those are separate pieces of work. The simulation I was showing this. Sorry. These ones, this one? Is that what you're thinking? Yeah, so this is an independent one where we're just using LV particles and a Galilei's favourite galaxy potential to show the formation of strings. Yeah, for the velocity distributions, we're extracting that directly from the island.
We have time for more questions. Nolan? You first and then.
So watching this movie, it appears that alien stars, ejectees, will be phase wrapped in 1 billion years. And so does that suggest that any ISOs we see, a very small fraction of them, will actually have originated from a star that's got anything to do with the local structure?
Yeah, so this is what would be, I didn't actually put all the plots up because this was, we're still kind of going back and forth on it here. But yeah, the degree to which it wraps and then you re-intercept either your own stream or streams that were formed near you. It does all things. So, but it turns out to be quite challenging to describe the volume of a stream. So it is going to be proportional to the velocity distribution cubed, but how it's going to be shaped, like they squish quite a lot, and depending on how eccentric the orbit of the star is in the galactic potential, that will stretch and fluff things quite a lot as well. So that has made it a bit challenging for us to parameterize this here.
And this is a smooth galactic potential, which the real one isn't.
Yes, that is the major point of work we're trying at the moment. So yeah, Agnes, for instance, one of the students is looking at the heating of the streams from giant molecular clouds, and then next after that we'll do the spiral islands.
Hi, just I'm wondering what the colors in
Oh,
the.
sorry, can you wait? I can't stop where you're at.
I'm wondering what the colors in the animation, previous animation of the galaxy are.
This one?
Yeah.
Yeah, so this is just here to give you an indication. So the stars are black, and then we code the ISO particles blue as they come on. And then for 3 particular stars that have different initial velocities in the galactic potential, we give them different colors just so you can distinguish how it moves. But yeah, like you can see this is a little bit fun once we actually scale this up, but it gets very detailed very fast.
So last question.
Okay, so we know that there are so many binary TNOs in our solar system. So how would this? Will we discover any binary interstellar objects, and how would they evolve in your model?
Ooh, that's right. If I have an extra slide.
Yeah.
Yeah. So, yeah, I'll show you this one to be honest. So, to give you some idea, so the model that we have at the moment does not include binarity, the kinds of things Rosemary was showing on Monday. But if you take this model and then superimpose it on the star, so the star here is the solar apex, the direction of motion of us in the galaxy. Gray is the model here. The problem is that if you're trying to test for binarity, I will point out that this is where we survey, and if you're going to test for binarity, you need to be very good at doing so in the galactic plane while they're inbound. And once they get close to perihelion is when you actually have a chance to be able to make that assessment.
Well, let us thank Rachel for her nice presentation.